not going to go full screen, I think. Let's see. Let's try this. All right, so let's just roll with this. Hi, my name is Kai Shang, and today I'll be talking about sketching linear classifiers over data streams. And this is joint work with Dr. Sharon, Peter Bayless, who's right here, and Greg Valiant at Stanford University. Okay, so linear classifiers are now an essential part of the modern data analytics pipeline. So to review, in binary linear classification, we have two classes, class A and class B, this way. And the goal is to learn a linear classifier, W, that separates these two classes. Okay, now linear classifiers are now ubiquitous, and they found application in a variety of settings, including spam detection, ad click prediction, network traffic classification, and many others. And part of the reason for their success is that they're very fast. So inference and updates to these models are very computationally cheap. And because updates are so fast, they're very well suited to these adaptive online learning settings where the classifiers are updated online in response to changes in the data. However, these high-dimensional classifiers come with a problem, which is that there is this fundamental tension between the desire to learn very expressive classifiers which use lots of features and are therefore potentially more accurate, and the memory needed to store the weights corresponding to each of these features. And this problem, high memory usage, really limits the applicability of these high-dimensional linear classifiers to memory-constrained environments. Okay, so as a concrete example, let's consider this problem of doing traffic classification with limited memory. And this is a problem that's been studied for a long time in the networking community. So here we observe some stream of network packets, and from each packet, we're going to extract some vector features. So for example, these features could correspond to prefixes of source and destination IP addresses. We're going to pass these features in through the classifier, and the classifier decides whether or not to accept the packet or to filter it. And frequently, you want to run this classifier on something, on a piece of network hardware like a network switch. And since the switch has very limited onboard memory, the goal here is to learn a classifier that adheres to strict memory budgets, for example, up to 1 megabyte of memory on the switch. But at the same time, you also want good accuracy, so you want to have lots of features. You want to consider, for example, interactions between features via feature combinations. And more broadly, we consider this problem of doing online learning on memory-constrained devices. So not just traffic classification, but also other types of classifiers that learn online on devices like your mobile phone, on smart home appliances, even down to IoT devices with down to 4 kilobytes of RAM. Okay? It turns out that this problem of restricting memory usage while preserving the accuracy of these classifiers is really non-trivial. And to see this, we can consider two possible approaches we can take in order to achieve restricted memory usage while preserving high accuracy. The first possibility is, let's just use the most informative features to learn the model. It's a very reasonable suggestion. The problem here is that in the streaming setting, we often don't know a priori which features are the most important. And more problematically, the importance of any individual feature can change over time. And very concretely, you can see this in the spam classification setting, where the spammer can introduce new terms and new strings over time in order to evade detection by the spam classifier. Okay, so this doesn't quite work. A second proposal is to only use the most frequently observed features. But here it's easy to see that the most frequently observed features are not necessarily the most informative. So by doing this, by only tracking the most frequently observed features in the stream, you can potentially lose out a lot in terms of classification accuracy. Okay, so what can we do? So what we do is we can turn to the streaming algorithms community, and it turns out that here there's been a long line of work on the use of memory-efficient summaries called sketches for various stream processing tasks. A very famous example, which was just touched on in the previous talk, is this problem of identifying the k most frequent items in a stream, otherwise known as the heavy hitters problem. And two well-known algorithms that solve this problem are the count sketch and the count min sketch. So the question we ask in this paper is, can we adapt existing sketching algorithms, such as those introduced for the heavy hitters problem, for use in memory-limited streaming classification? And the answer here is yes. So in our work, we introduce a new sketch called the weight-median sketch, which we designed for linear classification. And the weight-median sketch can be really understood as an extension of these previously proposed approaches for the heavy hitters problem. And the main intuition, the main idea is that instead of learning the sketch that tracks the most frequently observed items in the stream, we can instead learn a sketch that tracks the highest magnitude weights in our linear classifier. Okay, so more concretely, we can just draw this cartoon picture of what our sketch actually does. So as before, we have this binary classification problem with two classes. And we want to learn this classifier W that separates class A from class B. But instead of maintaining this high-dimensional vector W, which is potentially too costly in terms of memory, we instead maintain a memory-efficient sketch or a surrogate for this classifier. And as we observe new examples, we're going to incrementally update the sketch, like so, and so on. Okay, so there are two very natural questions that you can ask. One is, how accurate is the sketch classifier? Because after all, if it is not accurate, it defeats the whole purpose of this endeavor. And second, we can ask, how do the sketch weights relate to the weights of the original high-dimensional model, as if we hadn't done any compression in the first place? Okay, so these are both questions that we address in the paper. Now, let me just pause briefly to address the fact that there really is, unsurprisingly, a long line of related work for this problem that spans both machine learning and streaming algorithms. So I don't have time to go into this in detail. For more details, please see me after the talk or check out the paper. Okay, so let's talk about how the algorithm works. So the weight-median sketch can really be understood as an extension of the count sketch. So because of that, let's review very quickly what the count sketch actually does. So the count sketch is a low-dimensional summary or compressed version of the counts of items that have been observed so far in the data stream. And the data structure of the count sketch can be visualized as a two-dimensional array of counts. Okay? So I've drawn this here as this series of rows with S rows in the sketch. And let's say we want to update the sketch with an increment for the count of some item I. So the way we do this is we just take the item I and we compute the hash of it, S times, with S independent hash functions. This picks out a sequence of distinct buckets within the sketch. And what we do is we just simply apply an additive update to each of these buckets. And in particular, the additive update is just the value of the count increment multiplied by a random sign flip. So it's very simple. The weight-median sketch update is very similar. But instead of updating the sketch with a vector of count increments, we instead update the sketch with a vector of gradient estimates. And the second semantic difference here is that instead of maintaining a sketch of counts, we're instead maintaining a sketch of weights corresponding to the weights of the linear classifier we're trying to train. And it turns out that this procedure of updating the sketch with gradient estimates corresponds to just performing gradient descent on the weights stored in this sketch data structure. Okay? So the weight-median sketch update very closely mirrors the count sketch update. Now the count sketch also supports queries of the form, given some feature I, give me an estimate of how many times this item I has been observed so far in the stream. And the procedure for this is very simple. We're just going to hash this item and pick out the buckets that it corresponds to in the sketch. And we're going to compute a median of S values. And then it turns out that this value, this median that we return, is an unbiased estimate for the number of times this item has been observed so far in the stream. The weight-median sketch query is identical. But again, the semantics are slightly different. So instead of returning an estimate for the count of an item, we're instead returning an estimate for the weight of this, the weight corresponding to this feature I in the model. So intuitively, the count sketch gives us low error estimates of the largest counts we've observed so far, whereas the weight median sketch gives us low error estimates of the largest magnitude weights in the model. And I should note here that standard feature hashing does not, in fact, support weight recovery. So this is the main difference between this weight median sketch approach and standard feature hashing. So what can we say theoretically about the weight median sketch? Well, it turns out we can derive some theoretical guarantees on the weight approximation error. And the way we do this is we just compare the optimal weights for the original data and compare that to those recovered from the optimal sketched weights. Okay? And by optimal, I mean just the weights that minimize the empirical loss over the examples observed so far in the data stream. And given this, we can show the following theorem. And in English, what this says is the following. It says that with high probability, the maximum approximation error for any weight in the model is bounded by this quantity, which means that we can get good approximation for weights that are high in magnitude, or more precisely, weights that correspond to a large fraction of the L1 mass of the optimal classifier. And to do this, it turns out that all we need is a sketch of size polylogarithmic in the original dimensionality D, right? And so this means that we can potentially realize significant savings in memory because of this reduction in dimensionality. Okay, so this is pretty encouraging. Now, on a more practical note, I should mention that there is a very important optimization that we found that has to be done in practice in order to get really good performance. And that is this very simple procedure where, in addition to this sketch data structure, which is this 2D array, as you may recall, we also maintain a heap data structure that stores the highest magnitude weights in the model. And in practice, we find that this simple addition gives us significant improvements in both classification accuracy and weight recovery accuracy. And the intuition for this is that we're just reducing the incidence of bad collisions within the sketch. Okay, so how do we do in practice? We're going to evaluate the sketch on two metrics. First is classification accuracy, and second is how good we do in terms of recovering weights in the original space. So here we're going to compare the performance of the sketch in terms of classification accuracy versus the error achieved by an uncompressed logistic regression classifier. So the baseline of using only the most frequent features incurs a pretty significant increase in error rate at every memory budget that we test. Oh, so for those in the back, this is a bit hard to see. So on the x-axis, I just have a series of memory budgets spanning 2 kilobytes up to 32 kilobytes of memory. Okay? Feature hashing does slightly better. But it turns out that the weight median sketch does even better than feature hashing. And this is, in fact, a consistent empirical trend that we observe over all experiments, where feature hashing does slightly worse than the weight median sketch by a small but significant margin. So second, we have weight recovery, and here again, we have this frequent feature baseline. And here feature hashing does really badly, and the reason for this is that standard feature hashing does not provide any mechanism for accurate weight recovery. And the weight median sketch does a lot better in this metric. Okay, now in the remaining time, I want to quickly go over two real-world applications of the weight median sketch, and more examples are available in the paper. So the first is network monitoring, which is very similar in spirit to this traffic classification application that we covered earlier. So here we ask, given two flows of network packets that we observe simultaneously, what are the largest relative differences between these two flows? Okay? Now it turns out that we can just class this problem, this stream processing problem, which has been previously studied back in 2005, as a classification problem. And we can train a classifier that's compressed using the sketch. And then we can look at which features are assigned the largest weights in the classifier. And it turns out that the largest weights correspond to the features with the largest relative differences between these two streams. Okay? And we can show that this simple classification-based approach outperforms a count-min-based baseline by a significant margin. The second application is identifying correlations. So we want to find pairs of events which have a high probability of co-occurring together within a data stream. So concretely, within a text stream, these events could be the occurrence of individual tokens or words. And the co-occurrence are just co-occurrences of words within phrases. Okay? Again, we can cast this as a classification problem using the weight median sketch. And here we find that we can realize really significant savings in memory usage. So there is a standard approach in NLP where you just maintain counters for the occurrences of word pairs. And this takes almost 200 megabytes of memory. And we find that we can get a pretty good approximation, not perfect, but pretty good, for this problem using only 1.4 megabytes of memory using this sketching-based approach. And so what we show is that by accepting some approximation error, we can get over 100 times savings in terms of memory usage for this problem. So this is pretty good. I want to finish with some takeaways. And so in this talk, in this paper, we introduced the weight median sketch, which can be thought of as a count sketch, but for linear classifiers. Another way of putting this is that it's really an improved form of feature hashing. And I think the real promise of this approach is that it enables the deployment of these lightweight, memory-efficient classifiers really everywhere: devices, phones, smart appliances. The second main point is that a lot of tasks in stream processing can be cast as classification. And we find that for many tasks, we can realize significant improvements over existing approaches. And there's still probably lots of room for exploration in this regard. So I encourage you to think, can your own stream classification task be cast as classification? OK, so paper and code are online. Happy to take questions now. Thanks.
Thank you for the excellent talk and very interesting results. I'd like to ask a question about something that you did not explain in the talk. So you explained how to update the sketch, which is clear. So I'm just wondering, you would select which points to update your sketch with. So I guess, if I understand correctly, because maybe in the backseat, it's something like perceptron. You'll be maintaining sort of like a vector. And if I give you a point, you use your approximated vector to try to classify it. And if it's different from your prediction, then you use it to do the stuff that you did, right?
Right.
OK.
Yeah.
All right. Thanks.
All right, so the question was, how do we pick out which features to update? And that just corresponds to the features that are observed for the example that we're updating with.
Any other questions? OK, so let's thank the speaker again. OK, so our
Hello, everyone. I'm Li Bing Wang from Beihang University. This is a joint work with ETH Zurich, HKUST, and DD. Here's the outline. Let's start with background and motivation. With the development of mobile internet, spatial crowdsourcing becomes ubiquitous. It can be seen as a new way of organizing the crowd to do spatial tasks. Representatives include DD, Uber, Gatewalk, and Graham. There are mainly 4 steps in the workflow. First, some requester submits a request. He chooses his origin and the destination of his trip. Then the platform offers him a price. When the requester sees the price, he will decide if it exceeds his valuation for the trip. If it doesn't, he will accept the price, and the platform will assign an available worker to him, and also gain a revenue. Pricing serves an important step since it directly affects the user's experience and the platform's revenue. Next, we introduce some basic concepts and formally define the problem. In each time period, we are given as input a set of requesters or tasks R. For each R in R, it specifies its origin and the destination. The trip distance can be easily calculated. In addition, we assume it also has private valuations about the price per unit distance. The word private means we do not know its value, but it exists. For each worker W, it has a location and a radius. The radius determines the range of worker. The platform's goal is to set prices to maximize the total revenue. One share of the revenue is simply the distance times the unit price. And we also assume platform sets the same price for requester in the same grid. Here is an example. The bipartite graph is used to represent the relationship between requester and workers. Here, a price of $3 is offered to R1 and R2, and $2 per km to R3. After the decision, R2 refuses the price since its valuation is lower than 3. Finally, we do the assignment, which by default finds the matching with the maximum total revenue. Here is 5.9. However, if the valuations are arbitrary, the problem is so hard. Learning from previous works, we assume the valuations with regard to grid G are ID samples from an unknown distribution. If the CDF is denoted by FGP, the accepted ratios are defined as GP. An example is shown in the table. Now we try to maximize the expected total revenue. A price of $2 per km is offered to R1, R2, and R3. The expected total revenue is 3.9. We propose GDP problem. Given a set of tasks and a set of workers, the GDP problem is to find prices P for all grids to maximize the expected total revenue. Even if we know the accepted ratios, GDP problem is NP hard. Next, we present our solutions. Our framework is as follows. We start with special cases and extend them to the multiple grids. We first consider one grid with sufficient supply. We offer a single price P. The expected total revenue can be expressed in a concise way. Since the sum of DR is fixed, actually we only need to find the mass matter of PSP, also called the base price. As SP is a continuous function, we use discretized prices to approximate. Under a certain price P, the number of requesters who accept P follows the binomial distribution. So we can calculate the sample mean from historical records and obtain a table like this. Finally, we choose the mass matter as the base price, and in this case, a price of $2 will be it. The sample size shown here gives an epsilon error. And it's worth noting that always sticking to the base price gives an easy approximation. But if the supply is limited, there's no such concise expression. We use an approximation. The first term inside mean represents the expected revenue of R requesters, and the second one represents the revenue N works achieved at most. There are 3 cases for different numbers of workers. Only the third one shows a limited supply, and the mass matter moves to the intersection, which means a higher price is more suitable here. As long as the number of workers is clear, we can always find the mass matter. When there are multiple grids, we extend previous cases. We only add the sum and NG. But the amount of supply for each grid NG is actually unclear, since workers can move to the neighbor grids. We will use the matching-based approach to find better NG. Once they are specified, the mass matter PG can be obtained, and we maximize the expression of R. The basic idea is as follows. Initialize all NG at 0. In each iteration, find the maximum increase for the expression among those grids whose NG can be increased by 1. Here, if there's an augmented path which starts from some requester in grid G, there will be a worker assigned to that grid, and its NG can be increased by 1. We still use previous example. At first, N9 and N11 are both 0, so they are only discretized curves represented by the crosses. If some ng can be increased by 1, there will be a dashed line. Now we try to compare the increase between grades. We find grade 9 has a larger increase. We made this increase by modifying N9 as 1 and marking a request worker pair in the matching. Since there's no worker who can be the supplier of grade 9, there's only grade 11 left. We made this increase and the pricing is down. The expected total revenue is 4.1, which is larger than the case where we stick to the base price. We briefly present the evaluation results. We use real and synthetic data sets with settings shown in the table. The real data set is based on online test coding platforms in China. We compare 5 algorithms. SDE uses the supply and demand in exponents. SDR uses the ratio of supply and demand. Base P is a strategy where we always stick to the base price. And capped UCB is a strategy designed for one grid with limited supply. Here are the results on synthetic data. We can see MAPS achieves the largest revenue. MAPS is the most effective one. MAPS is also efficient. And here are the results on the real data. MAPS still performs best on real data sets. And finally, the conclusion. We propose a new problem called GVP. We designed several techniques with theoretical guarantees. It includes a sampling-based approach, a basic pricing strategy, and a matching-based pricing strategy. We conduct extensive experiments on both real and synthetic data sets. Thank you.